So in this problem, we're going to be using the drag force, essentially a free body diagram, in order to find a geometric parameter, in this case the angle at which a string would be held if we have a helium balloon sitting on that string in a crosswind. So we're going to start this problem out by drawing out the free body diagram and using really just what we would expect, based on kind of envisioning this situation in order to set up the problem. And then we're going to go through and plug in the different values of what we find um, from what we know in this class. Okay, so to start with, we'll start with our free body diagram. So let's consider we have this balloon sitting here. And we know that this balloon is filled with helium, so it's going to be feeling a buoyant force, F buoyant, that's going to be net upwards, right? Because helium is lighter than air, right? We're told that it's filled with helium, and it's sitting in um, air. Right? We have airstream velocity U is what's given. And so this balloon is also experiencing a drag force. We have some velocity U, which is moving from left to right, and so we have an aerodynamic drag as well. Drag. And now, if we were to uh, not tether this balloon, right, just based on that buoyant force and the aerodynamic drag, the balloon would fly away, right? So we need to have some kind of a string with some kind of a tension in it, or some kind of way of holding it. In this case, it's a string with some kind of tension in it. So we're going to have this F string. And our task is to find the angle of that string based on the velocity of the speed. And so to start with, we're going to say that we know that the force on the string in the x direction, that's equal to minus F drag. And we know that the force on the string in the y direction is minus that buoyant force. So another way of looking at this is if this is our net force on the string, we know that the y component is going to have the value of Fb, and we know that the x component is going to have a magnitude of Fd. And now the thing that we're looking for is our angle theta, and we can take that through, and we know that's the same angle that we have, internal angle that we have right here. And therefore, we know, for example, that tan theta is going to be our opposite over adjacent. Tan theta is going to be equal to Fd over Fb, or theta, the thing we want to solve for, is equal to the inverse tangent of Fd over Fb. Right, so now our question is, how do we find Fd and Fb? So let's start with Fb. Let's start with the buoyant force. That buoyant force is not going to depend on the free stream velocity at all. It's really just based on what we get from like a hydrostatics type problem. So the vertical direction, we're going to have Fb, that buoyant force. And this is just going to be the difference in density times gravity, right? So, times the volume of the balloon. And so we're given a diameter of 50 centimeters. So in terms of diameter, we'll have pi over 6 d to the third. And so we have air at 20 degrees C. We know that, let's see, so rho A is equal to 1.2 kilograms per meter cubed. We're not given the helium density, but we know that the helium pressure is 120 kPa. We're going to assume it's at the same temperature, so it's at 20 degrees C. So if we work this out, use our ideal gas law, know that the density of the helium is going to be the pressure, in this case 120 kPa, 120 kPa, so it's 120 to 3, 120 kPa over our gas constant times 293, so temperature Kelvin. And our gas constant, we're going to have R is our universal gas constant divided by the molecular weight of the gas. So in this case, that's going to be 8314. That's joules per mole Kelvin over the molecular weight, which for helium, you can look up would be 4.003 grams per mole. And so we'll end up with equal to 2077, assuming it's on units. And so we'll end up with a rho helium equal to 0.197 kilograms per meter cubed. And so if we now come back up to our FB, we'll have FB is equal to density of air minus density of helium, so 1.2 minus 0.197 times, let's see here, 9.81 times pi over 6 times 0.5 cubed. Let's see, and if we work that out, 1.2 2 minus 0.197 times 9.81 times pi by 6 times 0.5 raised to the third, we'll get 0.644 newtons. Right, so that's the first part of our problem. So now we have to find the drag force. And in part A, now we want to find the drag force at U equal to 5 meters per second. And we know that the drag force is going to be 1/2 times the coefficient of drag times the density times the area times the velocity squared. And it's important to note that the density, the relevant density here, is the density of the fluid that's moving around the sphere. Right, so this density here is going to be the density for air, not for the helium. Let's make sure you get cut off on that. The other thing to note here is that we don't know what this coefficient of drag is. Right, so we have to find this thing. In this case, you can go to table 7.3 of your textbook, and we'll see that for an ellipsoid, we're given an approximate value for the coefficient of drag based on L over D, or the length over diameter ratio for the ellipsoid. In this case, for a sphere, this is just an ellipsoid with L over D equal to 1, and so we have these values of 0.47 or 0.2, depending on whether the flow is laminar or turbulent. So this is interesting. This tells us that we actually have to first, before we can even figure out what the coefficient of drag is, we first have to figure out the Reynolds number, right? Which maybe we should have done right off the bat, just to get started on this problem, but certainly to find this coefficient of drag, we need to do so. So let's find the Reynolds number, right? So the Reynolds number, based on the, we'll do this based on the diameter of that sphere, is going to be rho u times d over mu, and this will be 1.2. Right, same thing we're using for the the buoyant force, times the velocity. In this case, the velocity in part A is 5 meters per second, times the diameter, which is just 0.5, over the viscosity. Viscosity, this is the viscosity of air, right? Because we're considering flow of this object in air, air flowing around this object. So that's going to be 1.8 times 10 minus 5 in SI units. So if we work this out, I'm running at 1.7 times 10 to the fifth, which certainly be turbulent if we had internal flow, but because this is external flow, this is still in the laminar region. Laminar, therefore, CD is equal to 0.47. So now we can find for part A, we find FD is equal to 1/2 times 0.47 times 1.2 kilogram per meter cubed, times pi over 4 times 0.5 squared. That's the frontal area of this sphere, times the velocity squared times 5 squared. Everything inside units. We end up with a drag force of 1.38 newtons. And now we're going to use our expression that we found for theta. So we're going to have theta is equal to tan minus 1 of the drag force over the buoyant force, or 1.38 over 0.644, or theta is equal to 65 degrees. Okay, that's our answer for part A. So now for part B, then we're going to want to know the drag force at U is equal to 20 meters per second. So again, we have the same expression, right? The drag force is just the 1/2 CD rho AU squared, but again, we don't know CD. And we're going to start by checking the Reynolds number. So we get RE based on diameter is rho U D over mu. So we have 1.2 times 20 times 0.5 over 1.8 times 10 minus 5. And so in this case, we have 6.7 times 10 to the fifth. Now we're in the turbulent regime. It's possible we'd have something like transitional flow. This is certainly greater than 5 times 10 to the fifth. We only have values for purely laminar, purely turbulent flow. In this case, that's given to us. And so since this is greater than 5 times 10 to the fifth, we're going to assume it's turbulent. And so therefore, for turbulent flow, and L over D equal to 1, we're going to have CD is equal to 0.2. Therefore, our drag force is 1/2 times CD, which is 0.2, times rho, which is 1.2 kilogram per meter cubed, times area, pi over 4, times 0.5 squared, times velocity squared, 20 squared. This works out to 9.43 newtons. And again, we're going to do the same thing. We're going to say theta is equal to tan, or inverse tan, of now 9.43 over 0.644. So in this case, we're going to get theta is equal to 86 degrees. So there we go. We used or what we know about actually fluid statics, which is how we find the net buoyant force on an object, as well as fluid dynamics of external flow, which is how we found um, the drag force on the balloon, in order to find the angle at which you would, a string holding that balloon up, or holding that balloon, sorry, tethering that balloon to the ground, or tethering that balloon to your hand, would be um, depending upon the free stream velocity. But again, another thing that I want to emphasize here, that we've emphasized a few times in class, is the importance of Reynolds number. Right? I've said this a few times, but you don't really know much unless you know the Reynolds number. In this case, just look at the difference in these Reynolds numbers for laminar or turbulent flow. Right? So if you didn't do that Reynolds number check and you just guessed, you could be off by, in this case, more than a factor of 2 on what that drag force computation was. So just as a reminder, make sure you know your Reynolds number, especially before you're using something that's tabulated like this, where we know it absolutely is going to depend on whether your flow is laminar or turbulent. All right, thanks very much.